In this video, we're going to talk about the complex logarithm. So recall a few things about the real exponential function, which we'll denote by exp, where you plug in any real number you like and you get a positive real number. And remember, that just takes Euler's number e, raises it to the x power. And we know that this is a one-to-one function, and it has an inverse that we denote by ln, whose domain is 0 to infinity, and it spits out a real number. And we call that the natural logarithm. So there's a little picture of the exponential e to the x with natural log of x next to it, the reflections of each other over the line y equals x. And thus y equals e to the x is equivalent to telling someone that natural log of y gives you back x. Some other things we want to remember about the natural logarithm. This function's continuous and it's differentiable on its domain for the positive reals, and the formula for its derivative is 1 over x. The next thing, the real natural log has some pretty nice properties, like natural log of x times y is equal to natural log of x plus natural log of y. The natural log of x to the r power is equal to r times natural log of x, and etc. Hopefully you remember a lot of those rules from like college algebra, say. And the last thing that I'll mention about the real natural logarithm is that it allows us to extend calculus rules that we know about e to the x to more general exponentials a to the x, where a is any positive number between 0 and 1 or larger than 1. And the way that we do that is by the formula a to the x is the same thing as e raised to the power x times ln of a. Now, on to complex. So let's let z be a complex number, x plus iy, where x and y, of course, are real numbers. The complex exponential e to the z, which we defined in a previous video as e to the x times cosine of y plus I sine of y. Remember, try to keep track of those. X is the real part of the complex number and y is the imaginary part of your complex number z. We know that this exponential is periodic with period 2 pi I. And so the complex exponential is not one-to-one. And that means that our job of trying to extend the real natural logarithm to the complex plane is going to need some special attention. So given a domain in the complex plane called A, what we want is to define a function, I'll call it fancy log here, from A to C, such that log of e to the z should give you back z for all z in your domain. But that just might not work. If e to the z is the same thing as e to the z plus 2k pi I for any integer, because again, it's a periodic function, then if I take log of both sides, those need not equal, because the exponents need not equal, especially when k is non-zero. So one solution to this little conundrum we're in is, why don't we think of fancy log here as a multi-valued function. So if you teach an algebra class, you're going to cringe. We tell our students there's no such thing. So one input can have many outputs. And we're just going to accept maybe that log of e to the z, okay, it's z, but also plus 2k pi I for any integer k. Let's take a little detour. So in fact, we've already considered a multi-value function. We know that there exists a positive real number r and a real number theta between minus pi and pi. So I'm saying you cannot be minus pi, but theta could be pi. Anyway, we know we could find two such numbers such that z equals r e to the I theta. In other words, z's got polar coordinates, and we're written in this complex form. And we're going to call theta the principal argument of z. And another notation for the principal argument of z is a capital A for arg of z. So again, when theta is between minus pi and pi, we'll call this the principal argument. But what we also know is that if I add any multiple of 2 pi to that, I just kind of wrap around, if you can visualize that in the plane. So that should also land at this point z that I'm considering. So r e to the I theta plus 2k pi is also a valid representation for this z, where k is any integer. And so thus what we've got is a multi-valued function, the argument of my complex number, which is equal to, we'll take the principal argument, but add any multiple of 2 pi to it that you like. Here's a picture of what's going on. And so what I've plotted for you here is our complex number, x plus iy. Those are the x and y are the first and second coordinates, but I've plotted it against what its argument is. And this is just to show you that any complex number, right, it's associated to, theta, its principal argument, but plus any multiple of 2 pi here. By the way, a graph like this is called a Riemann surface. You should check those out if you think these graphs are cool. There are some really cool ones out there. So that's the end of our detour. So we've already encountered a multi-valued function. You dealt with it in polar coordinates because you can wrap around the plane many times and still land at the same point. So we're going to accept that log of e to the z just gives you z plus 2k pi I for all integers k. So let's do a little example. So what if I've got e to the I pi, and remember that's just polar coordinates for -1. Let's apply log to both sides. And so what I'm saying is that should take e to the I pi, and it should spit out I pi plus 2k pi I, according to my formula above. And a visual representation here, what I'm saying is we're going to take our copy of the complex plane on the left, and it sends the input -1 to the many outputs in the right-hand copy of the complex plane. And notice that they're all separated by a multiple of 2 pi. And so also notice what that says is that, well, log of -1 is any odd multiple of pi I. And that's kind of crazy because already this complex logarithm, you can have negative inputs into this thing. Very different than the real natural logarithm. Now, what should log of z be? So just to backtrack a bit, we've accepted that log of e to the z is z plus 2k pi I, but what should a formula for just log of z be? What if there's no e there? So what we're going to do is we're going to write z in polar form, and we'll write it as r e to the I theta, where again r is the absolute value or modulus of z, whichever term you like, and theta is the principal argument, so between minus pi and pi. And again, I might denote that by capital A for arg in the future. And we're going to write our complex function in its real and imaginary parts, u plus iv, where u and v are functions of the variables x and y, or in my case, they're going to be functions of r and theta, again, real variables. And what we would like to have happen is that e to the log of z should give me back z, but maybe you have to wrap around. So maybe sometimes e to the I times some multiple of 2 pi. So there's a j there as well. So j is some integer. All right, so then let's kind of split this apart. Let's substitute u plus iv in for my log of z in the exponent, and what we're also going to do is substitute our polar coordinate expression in for z. And then what we can do is we can split apart that exponential on the left side with my exponent rules, and we can also combine the exponential on the right side with my exponent rules. And at this point, what I notice is that e to the u should be the modulus of the left side, and that should be the same thing as r. So those two have to match. And once they match, you can't cancel those out, and that says that the exponentials that you're left with, e to the iv and e to the I times all that junk in parentheses, those have to be the same. And be careful here, that doesn't necessarily mean that those two exponents have to be the same in number 2. What we can say is that v is theta plus some multiple of 2k pi. Sorry, theta plus some multiple of pi. Well, not just some multiple of pi, it could be lots of multiples of pi. And so what we've got is that, again, if I solve that equation there, on the left I started with u is the natural log of the modulus of z, and that v is just the principal argument plus some multiple of 2 pi. And so that's what we've got here is log of z should be equal to exactly that. Natural log of the modulus of z plus I times the principal argument plus 2k pi. That works for any integer k. And so again, that is the multivaluedness of the complex logarithm captured. Now what we can do is we can choose a specific value of k, and we can try to restrict theta to obtain a single valued logarithm. We're going to look at some ways to do that. So if I keep theta between minus pi and pi, as I've been doing, and if I take k equal to 0, then we obtain a logarithm called the principal logarithm. Notice I've picked a different color to denote this, and I'm also going to pick maybe a different font to write it in. So I'm not trying to write like the fancy cursive L anymore. Now it's just kind of a normal capital L. And the domain of the principal log is all non-zero complex numbers. When I say its codomain is the complex numbers, I'm not trying to suggest that this function is onto the complex numbers. I'm just saying that it spits out a complex number. All right, and again, notice here, this is defined for any non-zero complex number, and then that's, a pretty big extension of the real natural logarithm that didn't make sense to plug negatives or 0 into. All right, so the formula here would be log of z should be, again, the natural log of the real number modulus of z, how far z is from the origin, that's a real number, so you can plug that into natural log, plus I times the principal argument of z. And let's do an example. So the principal log of e to the I pi should be the natural log of the modulus of e to the I pi plus I times the argument, and that should be natural log of 1 plus I times pi, and we recover I times pi. And so notice again, that says that log of -1 is just I pi. And here, just to contrast with what we've done, we've obtained this logarithm spits out a single value, right? It's not I pi plus any multiple of 2 pi. It's just I pi here. So one problem with this function that domain, all non-zero complex numbers, that's way too big for the principal log to be continuous. And the reason for that is because, well, the argument of a complex number is not continuous along the negative x-axis. And we're going to look at this a little bit more closely. So let's let x be any real number that's negative. We're going to consider two sequences of complex numbers. I've got a blue sequence here that is x plus I over n, and I've got another one that's a yellow sequence here. I've denoted it by zn prime. Prime has nothing to do with derivative, it's just to denote a different sequence than the blue zn's. Anyway, the yellow sequence zn prime is equal to x minus I over n. And what we're going to consider, of course, is what happens as n gets very large. And what we see as n gets very large is, well, those two imaginary parts in blue and yellow, they get close to 0. So you should just approach x in either case. What I've got for you is a picture here. And what I want to notice maybe on the bottom first before you focus on the cool graph above. On the very bottom, it's just trying to say the blue sequence approaches x, from above, if you like, and then the yellow sequence approaches x from below. Again, so those imaginary parts are all negative is what I'm getting at. And now I look at this surface graph that's sort of in the middle of the screen right now. And it's the same picture, so try to use the 2D graph for reference there. What I want to notice is I'm plotting along with these blue and yellow complex numbers. I'm giving them a third coordinate that is defined by their argument. And I'm going to use the principal arguments of these numbers here. So if we're in that second quadrant where the blue points are, those all have angles that are between pi over 2 and pi. And then if you are a yellow number, you're in the third quadrant. So those all have angles between minus pi and negative pi over 2. And so what we're doing is we're plotting those angles as the third coordinate in the surface graph above. And what you see is that, well, as the yellow points get close to the x-axis, that argument gets close to minus pi. Whereas as the blue points get close to the x-axis, that graph's getting taller and its argument is getting closer to pi. And so that is exactly what we have written down here. And the point is that the limit, sort of like the limit from the left, isn't the same as the limit from the right in some sense. So I don't get the same answer there. And so that proves that this function can't be continuous. Now you might be wondering, like, okay, why is that bad? Your function's not continuous. Who cares? All right, so the principal log's not continuous on this domain. Well, then it can't be holomorphic there either. Remember, holomorphic was like complex differentiable with some extra. And, that's not good because that means that our principal log doesn't have the calculus properties that the natural log does. And so, sure, principal log z extends the natural log to the complex plane, but you can't do any calculus with it. That's kind of boring. It's kind of a disappointing ending. So one solution to this new problem is why don't we make the domain of the principal logarithm a little bit smaller. We're going to make it the complex numbers, but we're going to delete, that says we're going to delete the non-positive real axis. So all the negative and negative real numbers and 0, they get deleted. And so again, in red, that's what I'm telling you there. And if you need a visual there, I'm saying any point in the complex plane except for somebody on that red line, that's a legit point to plug into our complex logarithm. All right, so here our principal log would be continuous here, right? Remember that negative real axis was the bad part, so we're deleting it. What we can also do is we can also show that this makes the principal log holomorphic. So if we restrict it to this domain, we get a holomorphic function. And let's go ahead and show that. So the principal log, I know that it's the natural log of r, where r, remember, is the absolute value of z, plus I times theta, where I'm using theta now to denote the principal argument of z. And here u is natural log of r and v is theta. And you should check out the video that I did on the polar form of the CR equations in case you forgot. And so here they are, just in case you forgot them. And so those subscript notation, that's partial derivatives. So the partial of u with respect to r is 1 over r times the partial of v with respect to theta. And just to save a little time, I won't read the bottom one out to you. But you can use your formula up here to actually take those partial derivatives. So I can figure out what the partial of u is with respect to r, and etc. And just what do I end up getting? I get that those two equations hold as long as, I plug in a complex number that's in this legit domain, where I've deleted the negative reals and 0. So the CR equations work there. Now remember, that's not enough to say that your function's holomorphic there. That's a start. But what you also need is something like saying the partial derivatives of ur, u theta, vr, and v theta, those all should be continuous on the domain you're considering too. So this condition about continuous partials together with my function satisfying the Cauchy-Riemann equations on this domain, those two are enough to say that this function is holomorphic on this domain. Moreover, what should the derivative of the principal logarithm be? And so remember, again, the derivative is determined by the Cauchy-Riemann equations here, where I just use the partials of u and v with respect to r, and then times cosine of theta minus I sine of theta here. And again, we'll substitute the things that I know. You can compute UR, and you computed VR above. And when we do this algebra here, in the next step, we're going to use the even and odd properties of cosine and sine, where we can move some minus signs around or introduce one if we need to. And then what we can also do is we can use de Moivre's theorem in order to talk about integer powers of cosine of theta plus I sine of theta. We can take that negative inside, and that's really a negative power. And what I also did is you might notice, I took the 1 over r and I rewrote it as r inside the parentheses. The reason I did that is because I noticed that inside the parentheses, that's just z. And so this is just 1 over z. And that's pretty cool, because what we just showed is that the derivative of the principal logarithm of z is just 1 over z, just like it was in calculus. So that's a relief. Now here's a question. What's a tidy way of trying to restrict this multi-valued log to a domain and choose and arrange arguments for z to obtain a single valued function that's also holomorphic on this domain? So the answer to that question is to do what mathematicians do best, which of course is just make a definition. So the definition that you're going to encounter in most complex books about this topic is a branch of the multivalued logarithm is going to be any single valued restriction of that multivalued function to a domain where both 1, e to the log of z should just give you z in that domain, so it's single valued, and 2, that log should be holomorphic there. Some books just require it to be continuous because you get the CR equations for free. I'm just going to go ahead and say it's holomorphic. So for example, when I take the principal logarithm and I restrict it to this domain where I've deleted the non-positive real axis, and I take the principal argument of my inputs, so theta between minus pi and pi, we're going to call that a new word. We're going to call it the principal branch of our multivalued logarithm. Just to recap, I've said a lot of different principal this, principal that. This, whenever you just take your z's to be non-zero complex numbers, we're going to call this, and again, whose argument is between minus pi and pi, we're going to call that the principal value of the log, or the principal logarithm. But when we further restrict that domain to complex numbers that are not on the negative real axis or 0, then we'll call that the principal branch. And again, when you say the word branch, you're trying to tell somebody that your logarithm is also going to be holomorphic on its domain. So here's a question. How do you make other branches of the complex log? So one answer to that is to choose a different range for your angles theta. So let's do a little example. Let's try to compute log of e to the I pi over 2 and log of e to the minus I pi over 2. If our domain is as before, I still take my complex numbers except for the negative real axis and 0. But let's say that for this branch, I've also got that log of 1 is 4 pi I. What we're going to see is how to use that information. We're going to zoom in right away at the fact that that tells me that the argument of 1 is going to be 4 pi. So that log of 1 is 4 pi I tells me I'm taking the argument of 1 to be 4 pi instead of the typical 0 for a point that's on the positive real axis. And so I've got a little picture for you here. And what that's going to do, if I know that when I'm on the positive real axis, that angle is 4 pi, that allows me to get all the other angles that I'm going to need. So if I back up in yellow pi units or rotate backwards pi units, that tells me that the lowest angle I'm going to consider is 3 pi. And if I go counterclockwise pi units, that tells me the largest angle I'm going to run into is 5 pi. And those are actually kind of strict upper and lower bounds that I want to obtain. Because again, if you actually went that far, you'd be on the negative real axis, and you don't want that. All right, so then that ensures that you don't cross that red line when you measure theta. But what that's going to do is that's going to act like a reference for me in order to compute, well, what is log of e to the I pi over 2 up there on the positive imaginary axis? Well, you should just take your reference, you start at 4 pi, and I just need to add pi over 2 to get up there, and that takes me up to 9 pi over 2. And then similarly, what would e to the minus I pi over 2? Well, to get down to that negative part of the imaginary axis, I would start at 4 pi, and I would subtract pi over 2. So that angle would be 7 pi over 2. So what the logarithm should be 9 pi I over 2 and 7 pi I over 2 there as well. A little typo there. Those both need i's on there. It should be I times the argument. All right, and so another answer for how we can make different branches here is to choose a different branch cut. And a branch cut is a line segment that you have to delete from the complex plane. And notice that 0 is going to be on all the branch cuts of log of z. And you just might have a different branch point if you composed the logarithm with another function. Maybe you shifted that branch point around. Let's do a little example. Let's try to compute log of minus root 3 minus I if the branch for this is defined by removing the line y equals x, where x is a non-positive real number. So we're going to remove that part of y equals x from the complex plane. And I also say here that log of I is going to be minus 3 pi I over 2. So here's a little picture of where we are. And so I want to know what is the logarithm of that yellow point. But now here, this red line is the line we're not allowed to cross. And so what we'll try to do, though, is the same thing as before. We're going to use this information about log of I being minus 3 pi I over 2. That's going to give me some reference there. That tells me that when I'm there at I think of its argument as minus 3 pi over 2, not the typical pi over 2 that I would think about if this was the principal value. All right, so then that's going to give me something to work with. I use my formula for what the logarithm does. I know it takes the logarithm of, like the natural logarithm of, the modulus of my complex number plus I times the argument of my complex number. And so in order to get that stuff, well, I know to get down to that yellow, I'm going to have to go pi over 2 units from my reference minus 3 pi over 2, and I'm going to have to go another pi over 6 units to get down there. And so what this tells me then is I should just take natural log of 2 plus I times minus 3 pi over 2 plus pi over 2 plus pi over 6. And when you put that together, you get natural log of 2 minus 5 pi over 6. 5 pi I over 6. So given a branch of a complex logarithm, your typical algebraic rules need not hold. And this is one spot where, again, like the complex log is a little bit messier than the real natural log. So for example here, let's take the principal branch of log, and let's notice a little t-chart here. We're going to compare log of I times I minus 1, and what I'd like for that to do is to split, like log of I plus log of I minus 1. Let's go ahead and compute the left side of both. So log of minus 1 minus I, and remember we're using the principal branch, so I know how to measure the angle of this complex number. I would say that that's natural log of root 2 minus I times 3 pi over 4. On the other hand, let's go ahead and compute the logarithms in the right side separately. So log of I is going to be I times pi over 2, and then log of I minus 1 would be natural log of root 2 plus I times 3 pi over 4. Again, you kind of visualize I minus 1 is in the second quadrant. That's how I know I'm using 3 pi over 4. Anyway, what's the trick here? When I add those two angles together, I get natural log of root 2 plus I times 5 pi over 4. And so these two things, they're not equal. And so you've got to be careful. Your algebraic log rules need not hold for the complex log. Otherwise, though, complex log's pretty cool. It's holomorphic as long as you choose your branch carefully.